This video will explain the law of conservation of momentum, telling what it is, why it's true, and how you use it to solve problems, especially collision problems. You may remember this kind of problem from 9th grade. It's a collision problem with a before and after, and the before and after is separated by this vertical line. We have a larger object hitting a smaller object and they stick together. And the question is, find the speed or velocity of the combined mass after the collision. And you may remember that momentum is conserved. It's the same before and after the collision. And so you would find the momentum of this, mass times velocity, so 3 times 8. And you add the momentum of the other one, 1 times 0 since it's stationary, and you say that equals, oh look, afterwards they're stuck together. So here for the mass, we use the combined mass of 4 and times the velocity, which is the unknown, so we write the letter v. Then you solve this, and of course you get v equals 6 meters per second. If you want to make it a velocity, we say that, 6 meters per second to the right. We're going to go into more depth now in AP Physics than we did in 9th grade. So here's the general law, what the conservation of momentum is, what it says. For groups of particles or systems, if the total external force is 0, then something is true. And this, if you look at total external force is 0, you may think, okay, so there might be some force to the left, canceled by force to the right, up and down, and whatever. But usually there aren't forces. If we say the total external force on a group is 0, usually that means there are no forces. No external forces acting on the group. For instance, friction is small enough to ignore. Air resistance is small enough to ignore. Okay, so if that's true, if you have this group in isolation with no external forces acting on it, then the total momentum before equals the total momentum after, and we can write that this way. That's what the law says in symbols. Okay, why is this true? Well, now in AP Physics we go into more depth as to why this law is true. We did not do that in 9th grade. So we need some tools first. We need to refresh your memory on some tools you need to understand why this law applies. First, we need the third law, Newton's third law. And what that says is, imagine two objects, say, collide. And you have a force this way and a force this way. 1 pushes on 2 to the right, 2 pushes on 1 to the left. So we'll call this the force of 1 on 2, and this the force of 2 on 1. Okay? And what that says is that the force of 1 on 2 equals the negative of the force of 2 on 1. This is the equal and opposite law, that if object 1 applies a force to object 2, then 2 applies a force back on object 1 in the opposite direction with equal strength. And that's how you write this in vector notation, that these forces are equal, but the negative sign shows they're in opposite directions. Okay? From earlier in the chapter, we'll need the connection between impulse and momentum. Remember, it's not impulse equals momentum. The impulse on something equals the change in momentum of that thing. And I'm going to use subscripts here. The impulse, say, on object A equals the change in momentum of object A, just to focus that this impulse is applied to one object, and it creates a change in momentum of that one same object. All right? Well, I've been using the expressions impulse and momentum, but we better make sure you know what those mean. Impulse was defined as a time integral of force. So you take a force and you integrate it with respect to time from some initial time to some final time. And that gives you kind of the total dosage of the force. And momentum is defined as, familiar from 9th grade, the mass of an object times its velocity. All right, so here's how we prove the law of conservation of momentum. And by the way, this is Newtonian proof. This is not the way it'd be proved in modern physics. So we have familiar from freshman year, before collision and after collision. Two objects heading towards each other, they bang into each other, and afterwards they're moving away from each other. They have bounced. And in 9th grade, we only had before and after, and I said, we don't worry about during, it's too complicated. Well, now we're going to worry about the during process so that we can prove this. So let's take this and start talking about the during phase here. So we have object 1 and object 2. Each applies a force to the other when they collide. We'll call this 1, 2, and this 2, 1. So since this arrow is touching object 2, this means the force applied to object 2. The force that object 1 applies to object 2, and this arrow means the force that object 2 applies to object 1. Okay, well, by Newton's third law, we already said that these are equal and opposite. And you write that this way. That's how you write Newton's third law. It means that if this is, say, 18 newtons of force, this is 18 newtons of force, just in the other direction. Now we integrate both sides with respect to time to create an impulse. And we integrate it from the point that the contact begins to when it ends. And since if 1 is in contact with 2 for, say, 3 seconds, then 2 will be in contact with 1 also for 3 seconds. Those times have to be the same. So we integrate from when the collision starts to the final time when it ends on both sides. This is 1, 2, and this is 2, 1. So what we've done is take Newton's third law for this collision situation and integrate both sides with respect to time from the time when the collision starts to when it ends. We can do that's the same for both. That should be TF, because they're each in contact with the other for the same amount of time, and their negative sign comes down. Okay, these are impulses. So this is the impulse from 1 acting on 2, and it says that's the negative of the impulse from 2 acting on 1. And if you look at the previous page, look at what we've already written down, scroll back or whatever, and think of what impulse tells you about what happens to an object, you can see where this is going to go. You may want to pause the video and try to complete the proof. Okay? This is the impulse that acts on object 2. That creates a change in momentum for object 2. And this is the impulse that acts on object 1, and it creates a change in momentum of object 1 that's equal to that impulse. Okay? And there's a negative sign. So look what this says. Because the forces are equal and opposite, the impulses are equal and opposite, which means the changes in momentum are equal and opposite. Remember, these are all vectors, so if this change of momentum points right, this one will point left, for example. Now, let's add delta P. Add delta P1 to both sides, and look what you get. So, delta P1 plus delta P2 equals 0. There's a lot of symbols here, so let's pause and remind ourselves what these symbols mean. Change in the momentum of that ball plus the change in the momentum of that ball has to equal 0. So for instance, if this one gains momentum, then this one has to lose momentum. See, the change in one plus the change in the other cancels out to make 0. If one's positive, the other has to be negative. If one gains momentum, the other must lose, so that you get a total of 0. You can't get something for nothing. If you want to make the momentum of one of them get bigger, the momentum of the other one will get smaller if there are no outside forces acting on this system. So let's write this again and talk about what this means. Delta P1 plus delta P2 equals 0. These are vector quantities, which means if you change more to the right on this one will change to the left. For example, that's what the positive and negative would mean in one dimension. So we can think what this means. If one momentum increases, then the other momentum must decrease. Notice these are not delta P's, these are P's. So if the momentum of object 1 gets bigger, then the momentum of object 2 gets smaller. And by the way, remember these are vectors, which means we're talking positive and negative. So if one momentum gets more positive, then the other momentum gets more negative. That's another way of thinking about it. Okay, so in other words, i.e., that is, or in other words, okay, the total momentum of the group stays the same, stays constant, if there are no external forces. And there could be external forces, but they could magically cancel out and make a 0. That's rare. Usually this means that there are no external forces, as I said before. So if there are no external forces, then the total momentum of the group stays the same, or we say is conserved. And that's why it's called the law of conservation of momentum, is conserved. Okay, and this can also be written, another i.e., the total initial momentum equals the total final momentum. This is the most useful way to think of it for solving problems. That's my reminder that I start class soon. So we'll wrap this up, and I start my regular physics class in about 10 minutes. So this is another way of saying momentum is conserved. The total initial momentum equals the total final momentum. There's no net change in the momentum. All right, let's look at how you would use this to solve problems, right? The three things we're going to look at is, what is the law of conservation of momentum? Why is it true? And then finally, how do you use it? So here's some examples. And we'll look at these examples with the approach of gain and loss. What we were saying, that if one object gains momentum, the other must lose it. Okay, so in this first one, you can see the before and after. I won't bore you by reading everything to you. We'll just get right to it. We'll make the momentum of the larger object be in red ink. So this has an initial momentum of plus 30 and a final momentum of 10 kilograms of mass times 1 meters per second velocity, so 10. So that lost 20. So we expect the other to gain 20. So this has an initial momentum of 0. That 2 means object 2. There's no arrow. This is sitting still. Don't get confused and write that its momentum is 4. Its velocity is 0, so its momentum is 0. And this has a final momentum of 4 times 5, or 20. So this object 2 gained 20, and object 1 lost 20. That's the idea of conservation of momentum. That's built into the universe. And even though we've shown Newton's laws aren't strictly true, this is still correct. Even in relativistic terms, momentum is conserved. It's just that the idea of mass includes the idea of energy in relativistic terms, but that's not part of our course, so we won't discuss it any further. Okay, let's look at the second example. Object number 1 in red. This has a momentum of 12, and here 0. So it lost 12. This has a momentum of 0, object 2, and after it has a momentum of 12. So it gained 12. So red loses 12, blue gains 12. And finally, in this last example, this has an initial momentum. Red has an initial momentum of 200 and a final momentum of 160. So that's a loss. So that's lose 40. And then object 2 in blue ink has an initial momentum of 2 times 5. Oh, that's 5 to the left. So that's negative 10. Initial momentum is negative 10. Momentum's a vector quantity and it has direction. And then in the final picture, we have positive 30 for the momentum, 2 times 15. And so if you look at that, from negative 10 to 30 is gain 40. So see, this is a vector quantity. You can have negatives and positives, and the change can be to the left or to the right. The red object loses 40 units of momentum. The blue object gains 40 units of momentum. Now, I do not recommend you do problems this way, thinking of individual gains and losses. I'll show you what I think is the best way to do actual problems. Just use the idea of something being conserved, just like the previous chapter in energy. So your brain is well prepared to deal with conservation problems, and this is actually easier than the energy chapter because there aren't different types of momentum, and the formula is easier. So let's go through and do these problems. It's very simple to set them up, and just remember momentum is mv. And v can be left or right, positive or negative. So here we have 10 times 3 plus 0, right? Mass times velocity plus mass times velocity equals 10 times 1 plus 4 times v. Right? Each individual momentum is written down separately, and then the plus sign means the sum of the momentum on this side. That's what sum means. Equals the sum of the momenta on this side. That's the plural of momentum, is momenta. So we get 30 equals 10 plus 4v, and of course you get v equals 5 meters per second. Okay, let's look at this one. Here the unknown is in the before picture. That's okay. It's the same idea. The momentum of the first object is 20v, plus the momentum of the object is 2. Now what should I write for the velocity of this one? The answer is negative 5 equals 20 times 8, right, mv plus 2 times 15. And then just do the algebra. Minus 10 equals 160 plus 30. Let me pause and double check everything. 20v minus 10 equals 160 plus 30. So this is 190 plus 10 is 200 equals 20v, so v equals 10 meters per second. And then finally, in both of those collisions, the objects bounced. So finally, let's look at a sticking collision. Once again, total momentum before equals total momentum after. So 3 times 8 plus, is this momentum 1? No, it's stationary. There's no arrow. So its momentum is 1 times 0 equals, now what do I do? Well, these are stuck together, so they are now treated as one object with what total mass? So something times v, the total mass of this would be 4, a 3 and a 1, so 4v. That's 0, so you have 24 equals 4v, so v equals 6 meters per second. There's a practice handout that will be in topics, so it's just the same one we did in 9th grade. You should do that and check your answers, and then this prepares you to do homework number 4.